I think chemical equations and chemical reactions is kind of fun in chemistry, but I can tell you it's probably one of the topics that we'll discuss over the next month or two that's going to be one of the hardest to grasp, all right? Throughout my years of trying to teach this, I've tried to come up with a lot of different steps or shortcuts, just things to help you remember how to do what we're going to try and accomplish, okay? You saw a lot of chemical reactions take place in one lab. You saw copper 2 nitrate be completely changed over, and you were able to pull copper out of that and add aluminum ions to a solution. I mean, you did 3 or 4 different chemical reactions in one lab. And so that's fine. You can go ahead and do those in a lab when they're safe. But a lot of times it's not safe to do it unless you know what's going to happen first. And that's where chemical equations come into place. It's basically the written out form of what took place. Okay, so if you took this solution here and you mix this with it and some reaction took place and you got something new, that's what a chemical equation shows us. Okay, the first part's going to be easy. The first part is there's 5 of them. All right, in chemistry there's basically 5 different ways that chemical reactions can take place. Okay, so you're going to have to memorize a little bit. You get to memorize basically just not how to do something, but what those 5 are. All right, the first one you'll see on the screen, it's called a synthesis reaction. All right, and basically synthesis reactions, all they are is I take substance A and I mix it with substance B, and I get something that's now combined into something brand new. For instance, sodium and chloride ions. You take Na, you add Cl to it. If you can get those two to react, you're going to get NaCl. So pretty easy concept there. Take 2 things that are separate, mix them together, and you get something new out of it. Okay? Decomposition is just the opposite of that. If you look at decomposition, and I know I'm not using actual names, I won't do that quite yet. All I'm doing is using letters A, B, Y, and Z. But what you'll see here on a decomposition is that you've got something, you've got some material, it's made up of a couple of different elements, and you make it come apart, okay? So maybe you've got water, all right? If you send electricity through water, you can break apart those hydrogens and those oxygens, and you can break them up into their 2 components, okay? So that's a decomposition, taking something and pulling those pieces out. A lot of times you have to add energy to decomposition reactions to make those complete, to make one thing pull apart into its pieces. Okay. Single replacement reactions are a little bit tougher. What you'll notice is that you've got some substance A, and you've basically got it dancing. I used this the other day. It's hanging out at the dance, and B and Z are dancing together. Well, A comes in, and A's this big, buff, huge guy, and he walks into the dance, and Z looks over and says, oh, that's a better looking person to dance with. And so Z ends up dancing with A and leaves B high and dry in the dust. So single replacement reactions, this will make a little bit more sense when we start to tie in real chemicals that do this. But just all you got to know for a single replacement reaction is that you've got 2 things together, one separate, and they switch. Okay, leaving one that was once combined separated. All right, I'm going to skip forward to here. These are the last 2. All right, these are the last 2 reactions you'll be responsible for. They're called double replacement and combustion. All right, so if a single replacement was a dance, 2 dancers together, and this guy over here, and they switched, and then one of these was left behind, and this one now has a partner. Well, double replacement is kind of the same thing, except imagine 2 partners, 2 groups dancing. You got these 2 over here and these 2 over here. All right, they get separated, and one from here dances with one, and then the other one dances with the other guy, and so they just switch partners. All right, and that's a double replacement reaction. And those are actually pretty common. You probably did some of those in that lab with that copper 2 nitrate. So double replacement reactions are really common. Okay. And then finally, combustion reactions. You'll notice I've added some actual letters, some actual compounds. You'll see that there's some substance made up of carbons and hydrogens. They're called hydrocarbons. And anytime that you take that and you add oxygen to it, okay, and you have an ignition, some sort of, in the presence of oxygen, you ignite those, it's going to give off something. And these are called combustion. All right, and to combust, to either heat up or flames, okay, combustion. In the presence of oxygen, the O2, this thing called a hydrocarbon is going to break up, and it's going to break up, and from it, you're going to get carbon dioxide, and you're going to get water. And so that's the fifth kind, okay? In any of these, let me go back. In any of these, we need to throw a quick term in here, if I can find my mouse. These guys here are called reactants, and these guys here, what you either have made or pulled, whatever, after the reaction's taken place, these guys are called products. Okay, so at least before we call this a wrap, I want you to see at least one of each. Okay, this first one is synthesis. Let's do one. All right, we used this substance the other day. You used hydrochloric acid. Okay, and all that's made up of is hydrogen and chloride ions. All right, but what you have to do here is when we talk about chemical equations, you've got to write stuff out properly. Okay, you can't lose and gain material. All right, when hydrogen is hanging out by itself, if I could have a canister of hydrogen, H doesn't sit by itself. It hangs out as H2. And why does it do that? Well, because we talked that in the Lewis dot, it doesn't like to have just one single outer electron. It needs two, so it needs a buddy. And so it shares those two. That's why H2 is always that way. Well, chlorine is the same way. And I think we labeled these in class. We called them diatomics. All right, and this is one of them. I told you they made a 7 on the periodic table. There were 7 diatomics. We'll memorize them, okay? But chlorine also does not hang out by itself. All right, chloride ions have 7 outer electrons, and that's not good. It needs 8. So it needs another chloride ion to share a pair. All right, and so now he's got 8 and he's got 8. Well, you've got to write those in properly in here. All right, and then one of the things that we're going to cover next is balancing these chemical equations. And right now, this is not balanced. Okay, you've got 2 hydrogens over on this side that you started off with, and all of a sudden you only have 1 over here. Well, that doesn't fly. You didn't lose material when they came together. H's didn't just go float away. Okay, and so we'll talk about rules here in a second on how to balance. We may actually save it for a different lecture, but for now, just put a 2 in right here. Okay, that makes 2 HCl's, and that makes the numbers on either side the same. Okay, let's do a decomposition. Let's do water into its parts. All right, water's hanging out. We send some electricity through it. It's going to break up into H's, and it's going to break up into O's. All right, but what we know is that H doesn't like to be by itself. All right, and O is also one of the 7 diatomics. It's not happy by itself. Why? Because O has 6 outer electrons, and it needs 8. So it's got to share 2 from this guy. So it forms a double covalent bond, and it needs a buddy. Okay. So water broken up send electricity through it, forms into hydrogen gas and oxygen gas. And as you can see, the numbers are not correct. For some reason, we only have one O over here, two O's over there. Where'd those extra O's come from? They didn't just come out of thin air. Well, we would need to fix this, and we use numbers in the front to do that. And now I have 4 H's, 4 H's, 2 O's, and 2 O's. And we'll get to that later, okay? But just write it down as it is fixed, okay? Let's do a single replacement. Let's see here. Calcium. Calcium's good by itself. Hanging out there with water. Trying to make that a better too. There we go. And let's go ahead and switch dance partners. Like I said, that's what happens. Into calcium. And hydroxide. But we're going to go ahead and leave some H's high and dry. Okay? And so we've got basically just a switching of partners here. We've had something here, now he's partnered up, and we left some hydrogens high and dry. Okay? So there's a typical replacement reaction. All right? There might be some better ones than this, but that's good enough for now. All right, just get some examples down, that's all. Let's do a double replacement. We could probably get one from today's lab. Let me find that real quick. I'm going to write it in a different form. Copper 2 nitrate. One of the first things we did is we added sodium hydroxide. All right, and what did that form? Well, we switched partners. Okay, so what it ended up doing was forming copper 2 hydroxide. And what's left? Who's left? The sodium and the nitrate. All right. And then finally, a combustion. Some number of C's and H's making up what's called a hydrocarbon. And in the presence of oxygen, if they're set ablaze, you'll get a release of carbon dioxide and water. And this, you could really have any number of C's and H's, okay? What I'll do is I'll do this guy here, C3H8, all right? And the way it would look, balanced, is 5 oxygens, 3 carbon dioxides, and 4 waters. So, I'm not covering in this lecture what this is all about, all right? I'm not doing that. All I'm doing is telling you the 5 different types of chemical reactions that can take place. Either breaking something down, making 2 things come together, replacements, or combustion. That's all, okay? You've seen a couple of things. You've seen the formula form, like this. You've also seen the written out form, like that, okay? So that's as far as I want to go today. You've got 5 different types of chemical reactions and examples of each. That's all, okay? All right.